Hello students, Miss Slyman here. In this video I'm going to talk about complex conjugates. So if I have two complex numbers, not two, it's just one complex number, whoops. So given a complex number, a plus bi, its conjugate is given by a minus bi. So notice the only part that changes is the imaginary part. So the coefficient of the imaginary part changes sign. And I can think about this in remembering the quadratic formula. So quadratic formula, negative b plus or minus square root, and square roots are where I get my imaginary numbers. So it's the plus or minus that forms the pair, and so we call those a conjugate pair. If I have two complex numbers, a plus bi and c plus di, I find the quotient. So one way to find the quotient is, of course, just to write it as a quotient. But the thing is, mathematicians don't like imaginary numbers in the denominator. So just like you learned to rationalize a denominator, we can also realize a denominator. So if I multiply by the conjugate, well, there's this special property. So I'm going to multiply through by the conjugate of the denominator. So it's going to be c minus di. And the reason that I do it on the top and bottom is, of course, that's just 1. So I'm not changing the value of the fraction. I'm just putting it in a different form. I'm going to multiply out the top, and it's going to turn into some value, some complex number most likely. It's not likely to be real. It will almost always be some sort of complex value. And then in the denominator, well, when I FOIL this out, I'm going to get c squared minus d squared I squared, because this is a difference of squares. But of course, I squared is just negative 1. So that means the denominator becomes real. It's c squared plus d squared. My numerator is going to be that complex number again, whatever you get from multiplying it out. But now I have a real value in the denominator, and so that's what we say when we're talking about realizing the denominator. So in an example like this, where we say divide, really what I care about is that the denominator is real. So in this case, to make that denominator real, all I have to do is multiply top and bottom by I. So I'm going to get 4i on the top. I'm going to get 5i squared on the bottom, which of course becomes negative 5. And it doesn't matter where I put that negative sign, so I'm going to put it in front. One thing that I've seen people do is multiply by the conjugate by writing this in its full complex number form. So I could think of this as 4 plus 0i over 0 plus 5i. If I multiply through top and bottom by the conjugate of the denominator, I would multiply by 0 minus 5i. And that's going to give me on top negative 20i. On the bottom, I'm going to have negative 25i squared, which of course will become positive 25. And when I simplify this, I get negative 4i over 5. So I get the same thing. It's just that by inspection, I can see that all I had to do was multiply top and bottom by I. Over here, though, that's not the case. To make the denominator real, I'm going to have to multiply by 1 minus 4i. Because I do that in the denominator, I'm also going to do it in the numerator. Up top in the numerator, when I multiply this out, my real component is going to be 2. And then I'm going to have negative 3i times negative 4i will be 12i squared. 12i squared becomes negative 12. And now my imaginary bits, I'm going to have negative 8i. And then I'm going to have negative 3i. In the numerator, I'm going to end up with 1 minus 16i squared. Of course, that's going to become 1 plus 16. So collecting like terms, negative 10 minus 11i over 17.